All right. So next topic would be crystal structure. I think I mentioned medyo may sayop kanang piso and last video. So I think it's not oxygen, fluorine and chlorine, but oxygen, nitrogen and fluorine. So diri apilang chlorine. So you can see anyway, you can see that in your book and also in the LP. So nagkakamali lang po tayo. So okay lang 'yan. Ito ha. So anyway, you can read it from your LP and also from your book. This from your book text. So oxygen, nitrogen, and fluorine are the electronegative atoms, and of course you have your oxygen, hydrogen. You have still your oxygen, fluorine, and nitrogen bonded to that hydrogen, and then that hydrogen in that bond will form an hydrogen bond going to this molecule with these atoms. Okay. So that's what it means. See the explanation here. So after the hydrogen bonding, so we call that bonding a hydrogen bonding, one of the five intermolecular forces. Actually, after that, we have properties of liquids. I already talked already about this, and anyway, these are reading materials lang po to. So kindly read. What's the difference between adhesion, adhesion and cohesion? So, nandyan yan. Of course, the books has um, pictures, so it can explain more. Viscosity, yung lapot niya, another property of your liquids. Again, these properties are properties of liquids because of the intermolecular force. Okay? That that's what makes these properties are. So, kung alam niyo yung intermolecular force, basically it will somehow give you the idea, the physical manifestation of those uh, um, five different forces, namely dispersion forces, dipole-dipole forces, ion-induced dipole, dipole-induced dipole, and then you have your hydrogen bonding. So those are the five which gives rise to the properties. Of course, you have viscosity, you have capillary action, and dito yan. And then, yung water, it has a separate discussion because water really is unique. Unique. It it displays dipole, but since it has a hydrogen bonding as well, so that what prevails and what makes water really special. So I think the book is explaining here that water really with respect to solid, yeah, yun siya lang yung naiiba na when it comes to solid, the solid is less dense than the liquid phase. But most usually, yung iba or most usual, di lang usual sa atin kasi what we observe is usually water, liquid into solid. While other substances like when you're melting metals, plastics, basically the solid are denser than the liquid, making it making the solid material goes at the bottom. Okay, for a normal solid to liquid phase. Then water is discussed here. How come that it forms like that? Of course. Then after that, we goes to crystal structure. Again, the definition of your crystal structure, of course, your crystals as a predefined or well-defined order of atoms. So that's what really crystal structure is. Now, when atoms or any compounds in a solid state, so basically, since they cannot move, so we have to define the arrangement. So crystalline is the arrangement where it is well defined, while amorphous is the arrangement wherein it is not really defined. Meaning there are probably random arrangement of molecules. Basically, ionic substances are at room temperature are crystalline in nature, meaning they are well defined order. That's also the reason why it has uh, some of them has a particular color. Mm. Yes, most of them has white. Maybe that's also the I think being white is okay. Excuse. ah. Anyway, let's just follow the book. So for crystal structure, we usually investigate a unit cell. So if that is a repeating order, so one of the basically, if you can imagine anything which is complex and then looking at the single entity of it. So for a crystal structure, the single entity is we call it a unit cell. Unit cell. It's like a cube. It's like a defining some atoms as containing those particular cell. Why? Because that's what the concept is. You look at the whole structure of atoms and then you find a particular entity where it is repeated. So they call it a unit cell. The basic repeating structural unit of a crystal solid. So first is we have to know packing spheres. So since we will be discussing simple chemistry, so we will just be talking about simple cubic structures. It looks like a cube, but of course it has different alpha, beta, and gamma for us to understand that it is not just a 90 degrees. So it's not really a cube, but we call it simple cubic because maybe alpha and beta is the same, but gamma would not be, meaning it is inclined the z-axis, probably. But anyway, the general categorization for simple cubic, since from simple cubic we would be, I think we would be looking at three types of unit cells. Of course, there are some. Uh, in fact, there are 7 types of unit cells. But of course, we'll just be looking at simple cubic, and there are three that we will be investigating. So that's for us to be so that it would not be complicated because we'll just be scratching the surface for solids. I mean, in terms of concepts. So for simple cubic, so this is how they envision why simple cubic. So you can just if there is an order, you can look for the order and then look for the minimum or the optimized version wherein you can find a repeating pattern. So they call it cell. Now for simple cubic, there are 3 types basically that they have found. So these are the simple cubic, the body-centered cubic, and the face-centered cubic. So the difference between them is, of course, when you have a simple cubic, it's just like an 8 atoms seated in a corner of a cube. So if there are, that's one thing you can remember. You have to take note because um, those spheres in a cube uh, will tell us how many atoms really in one unit cell. So this is a body-centered cubic structure. Of course, the difference is it has one atom at the center. Um, Maybe your question is how come it's like this? So it's what the mathematicians found, or the chemist, or the scientist, or the physicist found, where they when they tried to look at the repeating patterns. So for simple cubic, again there are 7 at the top, and then we only focus on one simple cubic, and there are 3 of them. So body centered, it's just how they found out. Okay, so this is their study, or whoever um, is mastering actually this is the entrance to material sciences, wherein you can explain the metals, the properties of metals, properties of like uh, the new technology nowadays, the nanomaterials, especially. So this is the basic material science. Then you have the face-centered cubic. You can see that there are atoms at the face of the cube. So this is at the this you have this face. I mean this one at the center. This one is at the face of that on the other side. So if there are 6 faces, there are atoms on those 6 faces. So that's why 1, 2, 3, 4, 5, and then 6. So there are 6. There are also that 8 atoms in the corners. So that's what a face-centered cubic is. A body-centered cubic is the 8 at the sides and there is 1 at the center, while the simple cubic has 8 on the sides. The difference. So there's a definition of your coordination number. It is the number of atoms surrounding an atom in a crystal structure. So basically, for the application of this for a simple uh, coordination number. Anyway, you can read that in this um, uh, this text. Anyway, we'll just read that some other time if there are real applications on that. But anyway, you only have to count. I think that's the notion. For example, how many atoms are there inside this simple cubic? The answer is there's only one, because this center spheres, I mean these spheres at the corners will be divided into three. Okay, so if that sphere will be divided into three, um, the 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 space that would be attributed to that particular cell would be 1/8. Okay, so 2 divided by into this one, you divide it into 2 and then you divide it into 2, so that is basically 2 cube and that is 8. So meaning you divided it into 1 all over 8. So this would be 1 all over 8, 1 all over 8, and there would be 8 of those. So 1 all over 8 times 1/8. So for a simple cubic, there is a particular, I mean, there is a corresponding 1 atom per unit cell. For a body-centered cubic, there is already 1 at the center, and there's still that 8 at the corners. So 1 plus 1 for all those corners, which is 1 over 8. 1 over 8 multiplied by 8 would be 1. And then you have another 1 at the center, which is not waray maibani. Okay? So that is counted as 1. So 1 plus 1, that should be 2. So there are 2 atoms in a body-centered cubic. How about for a face-centered cubic? You have to realize that the atoms at the face is only divided into 2. Of course, the half of it is of course counted in that unit cell, while the other half is counted on the neighboring unit cell. So that's what a unit cell is. So if that is half, there are 6 of this. So there is 3, counted as 3 atoms at the face of a face-centered cubic, and there's still that 1/8 at the corners. So 8 of this, 8 of those, times 8, 1/8 times 8, that would be 1, plus 3 at the face, which are half actually at the 6. So based on a face-centered cubic, it has 4 atoms per unit cell. So again, 1 atom per unit cell, um, 2 atoms per unit cell, and this one has 4 atoms per unit cell. I think that's the important notion for simple cubic, body-centered cubic, and face-centered cubic. Okay, and then see, it is being divided into for a something at the face, it's already divided into 2. The other one is considered on that cell, while the other one is considered the other cell. That's why it should be counted as uh, 1/2 for the face. How about for the sides? It should be counted as 1/8. See, because your sphere would be divided into 8. So the only portion that would be included in that particular cell, because there are 8 cells in this one, of course, for a whole, they divided the whole atom into 8. That's why they have 1/8. Okay, so that's what the explanation is. Um, Closest packing, just read those. Anyway, my concern here is really this one. So after this, doing the mathematics of all of that, we can also say that for a simple cubic, this is a relationship between the atoms in a cell, because from a unit cell standpoint, we can actually identify, from a unit cell standpoint, we can already identify some of the properties. Like in this section, we will be talking about density, because density from the definition is the mass per unit volume. So since we can already, if we are given a particular solid, and then we know what elements compose of those solid, so we can look up at the periodic table, and then since we already know how many atoms there are per unit cell, we can already find what is the mass at that unit cell. Yes, we can already do that. Given that uh, a particular substance or a particular element is named as, let's say, SCC. So for an SCC, you can already identify one unit cell of that particular substance or element, the mass of a particular cell. Did you get it? Because you can already count the atoms. From the number of atoms, you can now exploit the Avogadro's number. Then you can count the how many mass. What is the mass? If an SCC simple cubic structure has one atom, so one atom of that, of course, you multiply it with the Avogadro's number, you can find how many mass for that one atom in a unit cell. The same is true with a BCC and an FCC. So if you already know the mass, you can already relate it also to the density. Since density, you only need the volume. Now you can already compute the volume because the volume is just the occupied space by those atoms. So if the atoms already mathematically um, modeled, so we can see that for an SCC, that distance between atoms with respect to the radius of the atoms is already found out as A is equal to 2R. So that's the difference. Because now, for a cube, we know that the volume of a cube is A cube. Okay? A cube, same is true with a BCC because they are all cube. Again, to make the computation simpler, since they are all cube, all the volume here is A cube. Okay? That is your side cube. And your side is A. But now we have to relate the A with respect to radius, and this is the relationship. A is equal to 2R for an SCC. For a BCC, A is equal to 4R over square root of 3. And for an FCC, A square root of 8R. So we can derive that actually, but we don't have any time. So we'll just use those formulas if the problem tells us that is an SCC, BCC, FCC, and so on and so forth. Here, there's an example in the book, and I will also look for examples. I think I already included this from the LPs, so I will be solving from the problems in the book, or probably from the problems in the LPs, so that it would be not redundant. Okay, so may I go to the may I see how long? Since it's already 18 anyway, I'll cut first the video and then I'll go. I'll be back.